if you turn to page 44, you have this graph of y equals, or f of x equals x minus 1 squared. If you have x minus 1 squared, does it make sense from our transformations unit? All this is a parabola moved 1 to the right. But it has only one x-intercept. So if I rewrite it like this, x minus 1 times x minus 1, can you see that your y-intercept, if you plug in 0 for x, you get 0, 1. And your x-intercepts, if you plug in 0 for y, and you solve this, you would get x equals 1, or, also x equals 1. So you only have one x-intercept. But you have one x-intercept that happens twice. See how the x equals 1 happened twice? And we're going to use the word multiplicity for this. That x-intercept has a multiplicity of 2 because in the equation it shows up twice. And it just so happens that when you have a multiplicity of 2, and we can write this off to the side, that if you have an even multiplicity, the graph bounces at the x-intercept. It bounces off of your x-axis and goes back up. And for odd multiplicity, because here we have our x cubed graph, x minus 1 cubed from your transformations unit. Do you see that this is just an x cubed graph moved 1 to the right? Technically, its equation looks like this, x minus 1, x minus 1, x minus 1. And if you set it equal to 0, you would get an x-intercept of 1 with a multiplicity of 3. So we're going to look at odd multiplicity. And we have to do this one in 2 different steps. We're going to start off with an odd multiplicity of 1. Which is not really a multiplicity if it happens only once, but it's terminology-wise, we say a multiplicity of 1, even though that's sort of contradicted. Multiplicity of 1 is what we had in this example. Do you see that each of these x-intercepts happens only once? And if they happen only once, your graph goes straight through all of those x-intercepts. So as a note, odd multiplicity of 1, the graph goes straight through the x-intercept. But if we have an odd multiplicity bigger than 1, of 3, 5, 7, and so on, you can either describe it as the graph bends, or this is a really nice one, or flattens out at the x-intercept. It's actually one of the major differences between the tan graph and an x-cubed graph. An x-cubed graph, actually you can draw a little tiny flat line there. It flattens out for 1 millisecond, completely flattens out. And the tan graph is more, the tan graph actually never flattens out, sort of technically doesn't get flat at all at that point. So they look similar, but they look similar just because we didn't pay attention to details when we graphed at the beginning. And we didn't make our x cubed graphs really flattened out. If you look back at some of your x cubed graphs from your first unit, they're probably not very flat at that moment, but they should be. Okay. So this is how multiplicity is going to help us. And if we look at our first example, sketch the graph of each one. Oh, and then we go to our examples. They're already factored for us, which is super nice. You can easily find the y, well, not as easy. The y-intercept is a little bit more math now. You have to actually plug in 0. And you get 1 to the power 4, which happens to be 1. Plug in 0 and you get -2. And then you have to multiply 1 times -2. So it's a little bit more work to get -2. This one is even harder. The y-intercept, if you plug in, here I'll even show with my work. If I plug in a 0 for x, I get 1 cubed, which is 1, times the -3, times the negative out front. My y-intercept is 0, +3. So it's no longer just the last number. You actually have to do the math. But your x-intercepts are a lot easier now because it's already factored. You have an x-intercept at -1, 0. This one has a multiplicity of 4 because of the exponent of 4. Multiplicity of 4, that's even, that's going to be a bounce. And our other one at 2, 0, that is a multiplicity of 1. Our graph is going to go straight through at that point. The other thing that we have to think about is what kind of graph is this? When it's factored, it's a little bit harder. Okay? Now I'm going to write it out like this for you. Okay? X plus 1, x plus 1, x plus 1, x minus 2. And if we wanted to write this out, does it make sense that if I look at all of my first ones, that I would have an x to the 5 and then a whole bunch of stuff after that? And since this is an x to the 5 graph, end behavior acts like a line, opening up. Not opening up, but going up from left to right, like a positive slope. So now when I go to graph this, my y-intercept at -2.
Wait, this is the wrong class, sorry.
X-intercepts at -1 and at 2. And behavior has to start down here. It's going to bounce off of that one and end up here. Sure looks like an x cubed graph, but it's an x to the 5 graph. For part B, the x-intercepts on part B are going to be at -1, 0. This one has a multiplicity of 3. That's going to be a bend. It's going to flatten out. And 3, 0, multiplicity of 1. Which means it's going to go straight through at that point. And if we wrote it out, g of x is equal to -x plus plus 1, x plus 1, x plus 1, x minus 3. And I look at all my first terms. All those first terms are going to have an x to the 4, but then there's also a negative out in front. Does it make sense that this is going to make a negative x to the 4 graph? Which, as a parabola, there's our end behavior. So when we go to sketch this one, what do we have? We have a y-intercept at 3. 1, 2, 3. An x-intercept at -1, and an x-intercept at 3. And because the -1 is a bend, and it flattens out, what I'll get you to do there is just draw a small flat line. Then when you do your end behavior, if I'm drawing my graph and I connect to that flat line, go through my flat line, and then straight through, it really bends at that point. So drawing a tiny little flat line will force yourself to make your graph bend at that point. If you just draw it straight through, it's an automatic 1-mark deduction, because this is a concept from grade 12, and you made a mistake. So anytime we make a mistake from a grade 12 new concept, it's going to always be a 1-mark deduction error. So drawing that little flat line really helps you make sure that you got that bend in place. Okay, questions for practice. 9, 10, 11,